All right, good morning, guys. So we are going to officially start Module 2 today. So as you come in and get settled, go ahead and put your phone away and complete the bell ringer in Canvas if you haven't already done that. Pause the video, take care of that, and come back when you're finished. And then finally, join the presentation by going to joinpd.com and using the code up here at the top right. That's SNSGMO. Okay, so this is a mandatory step. That way I can monitor who is participating in the lesson, who is actually trying, and I can give you feedback on your responses. Okay, and then thirdly, get out paper and pencil to write down notes, questions, and work example problems, because the more you write, the more you remember. All right, we are in Module 2 now, so we're going to begin talking about the periodic table, how it's arranged, how to use it as a resource, and quantum mechanics. So we left off with Rutherford's model of the atom, and we're going to learn here in just a bit that that model of the atom isn't necessarily 100% accurate. So quantum mechanics is going to explain why that is not 100% accurate and what we did to fix it. Okay, and this is section 1, quantum theory and the atom. All right, we left off on this video. We stopped this video last time at about 5 minutes and 25 seconds in. So go ahead and pause this video and go to your slides and start this one, but skip to 5 minutes and 25 seconds in, and then just watch the rest of it from there. It's going to talk about the rest of the development of the atomic model as we know it today. And I'm going to go ahead and skip that. Okay, we have two objectives for today. So number one is use the Bohr model of the atom to describe the relationship between the ground and excited states of an element in terms of absorption and emission of energy. We're going to learn about that first. And then finally, understand the organization of the periodic table as a pattern in terms of families, orbital shapes, valence electrons, oxidation numbers, reactivity, and other properties. So we're going to talk about how the periodic table is organized today. Review vocab. So atom is the smallest particle of an element that retains all the properties of that element and is composed of protons, neutrons, and electrons. All right, here's our new vocab. We're going to go over all these today. So ground state, quantum number, Heisenberg uncertainty principle, all the way down to energy sublevels. So just familiarize yourself with those words. They'll be covered here in this lesson. All right, so let's talk about the atom and some unanswered questions. So we left off on Rutherford's model, which had just a nucleus in the middle with protons, and it had electrons somewhere on the outside of the atom. And you know, all the mass was concentrated inside the nucleus, and electrons just kind of moved around it. But this model does not explain how the electrons were arranged around the nucleus. So as far as Rutherford's model is concerned, it can be fairly random. And this model also doesn't explain why negatively charged electrons aren't pulled into the positively charged nucleus. We know the nucleus is positively charged, and we know that oppositely charged things attract. So why don't the electrons, which are negative, attract to the positive nucleus and just kind of collapse the atom on itself? We know that doesn't happen, but Rutherford's model doesn't explain why. All right, so in the early 1900s, scientists observed certain elements emitted visible light when heated in a flame. So if I take a certain element and I put it in a flame, it's going to give off a certain color. And they were able to analyze that light, and that revealed that an element's chemical behavior is related to the arrangement of the electrons in its atoms. So the way an element's electrons are arranged determines how that element behaves chemically. Here's a cool little video of that in action. So you can see this guy's got different salts. He's got lithium chloride, strontium chloride, sodium chloride, copper chloride, and potassium chloride. And he's going to take a flame and light them all on fire, and you can see the different colors that they emit. He explains why that happens in this video. So take a second and watch this. Come back whenever you're finished. All right, here's another video of Professor Dave on YouTube. He talks about how electrons and light are kind of waves, and they're also kind of particles simultaneously. They kind of behave as both. They have properties of both. And this can be kind of confusing. So watch the video just to kind of be introduced to it, but don't stress so much if it's confusing, because it is. All right, Bohr's model of the atom. So now we have a new up-to-date model of the atom that's going to try and explain those things that Rutherford's model missed. And in Bohr's model of the atom, there is a lowest allowable energy state of an atom. And that lowest allowed energy state is called its ground state. All right, imagine that you're just, you're relaxing after a long day. Maybe you're laying down and you're going to sleep, and you have the least energy that you can possibly have. That would be your ground state. Okay? When an atom gains energy, it's in an excited state. All right? So once you wake up and you're ready to go and tackle the day, maybe you have an energy drink or something, you gain some energy, and now you're in an excited state. So Niels Bohr, the guy who Bohr's model is named after, correctly predicted the frequency lines in hydrogen's atomic emission spectrum. In other words, hydrogen is going to give off some light when it's heated, and Niels Bohr, based on these energy levels, was able to predict what color lights were going to be given off from hydrogen atoms. So I want you guys to take a second and respond to this question. Imagine a worker climbing a ladder. Number one, does it take more energy for the worker to climb to the middle or to the top of the ladder, and why? And finally, number two, suppose the worker dropped his hammer from the top rung of the ladder, and later that worker dropped the same hammer from the middle rung. Which level did the hammer hit the ground with more energy, and why? So take a second to answer those questions, and then come back. Okay. So if you said that it takes more energy for him to climb to the top, that's correct, and same with more energy dropping the hammer from the top. And the reason being is because you're further off the ground. So if this is the ground and I'm here and I fall, it's not going to hurt as bad as it would if I fell from like up here, right? So the higher you are, the more energy you have. And it's kind of the same with atoms, really, and electrons. So Bohr suggested that an electron moves around the nucleus only in certain allowed circular orbits. A lot of people call this like the planetary model, where the nucleus is sort of like our sun, and electrons are sort of like the planets in our solar system that orbit the nucleus, right? So each one of these is an energy level, and the one closest to the nucleus is the lowest. As you get further and further from the nucleus, you get more and more energy. So an electron close to the nucleus right here would be in the ground state, and then as it gets excited, it jumps up an energy level, and it would be in what you call the excited state. Okay? All right, and each of these orbits, each of these circular orbits was given a number, n, called the quantum number. And hydrogen's single electron, hydrogen only has one electron, is in the n equals 1 orbit in the ground state. So n equals 1 orbit is the one closest to the nucleus, and that's where hydrogen's electron lives. If that electron gets excited, it might go up to n equals 2 or n equals 3, and eventually it's going to come back down and emit light whenever it falls back down to its ground state. Okay? But each of these orbits is given a quantum number n, and 1 is closest to the nucleus, and then it counts out as you go further and further from the nucleus. All right, and when energy is added, the electron moves to the n equals 2 orbit, kind of like I just mentioned there. All right, here's another brief video of the hydrogen emission spectrum. It's like a minute long. I would watch this because it shows how hydrogen gas responds whenever you put it in a flame like this. All right, so Bohr's model explained the hydrogen spectral lines. It explained what colors hydrogen emits whenever it gets to an excited state, but it failed to explain any other element's lines. So there were still flaws in this model of the atom. As a matter of fact, the behavior of electrons is still not fully understood, but it is known that they absolutely do not move around the nucleus in circular orbits. Okay, we know now that electrons do not move around the nucleus in perfect circular orbits. Okay, so I want to ask you this question. Look at this chart up here at the right. Which color photon is emitted when the lowest amount of energy is released? So each of these arrows represents a certain amount of energy that's released. So which color is the lowest? And then which color is the highest? Okay, pause, take a second to answer that, and come back. And if you said red is the lowest, then you've got it, okay? Because each of these lines is another amount of energy that the electron or that the energy has to fall. So this would be like the lowest energy state. This would be the next one up, and then the next one up from that. So if it falls 1 level, it's the lowest. If it falls 4 levels, it's the highest. All right, next. Okay, so let's talk about the quantum mechanical model of the atom now. So there's a guy by the name of Werner Heisenberg, and he showed that it is impossible to take any measurement of an object without disturbing it. So if I got my phone here and I wanted to measure it, I'm going to have to touch it and move it around and interact with it. I'm going to have to disturb it. And that's true for anything. That's true for even particles. So he comes up with his Heisenberg uncertainty principle, which states that it is impossible to know both the velocity and position of a particle at the same time. So I can't know where exactly a particle is and how fast it's traveling at the same time. It's just impossible to know for something that small. The only quantity that can be known is the probability, or how likely you are to find an electron in a certain area around the nucleus. All right, so now the only quantity that we can know about a particle like this is the probability for an electron to occupy a certain region around the nucleus. And here's kind of a picture of what that looks like. So here I have an electron that is at rest, speed equals 0. So if it's not moving, I can know its position. But let's say that a photon collides with it, and a photon is just like a light packet. Okay, it's a packet of energy. All right, so it's going to hit this electron. Now the electron is moving, and maybe I can know the speed of the electron, but then I can't know exactly where it is at a certain point. So this is kind of showing that, and it shows the deflection here before and after the collision. All right, and then there's a guy by the name of Erwin Schrödinger. So Schrödinger treats electrons as waves in a model called the quantum mechanical model of the atom. Okay, and his equation applies equally well to elements other than hydrogen. So where Bohr's model fell short on other elements besides hydrogen, Schrödinger comes in and picks up the difference and says, all right, now I've got a model that is good for hydrogen, but it's also good for other elements too. Okay? And his wave function predicted a three-dimensional region around the nucleus called the atomic orbital. So no longer a perfect circular 2D orbital, but a three-dimensional, almost like spherical atomic orbital. So this is a dot representation. The more dots you have clustered in an area, the more likely you are to find an electron there. And here it is just kind of represented as a solid shape. So it looks like a sphere. You can see it's three-dimensional here. Okay, so this is an atomic orbital where electrons would kind of hang out. All right, remember that quantum number n that showed the energy levels around the atom? We're still talking about energy levels here. So the principal quantum number n indicates the relative size and energy of atomic orbitals. So the bigger n is, the more energy, and the bigger the orbital is. N specifies the atom's major energy levels, called the principal energy levels. Okay, so we call them principal energy levels because they are the first number that we report whenever we're talking about where electrons can live in an atom. So principal energy levels, if it's energy level number 1 or energy level number 2, that's going to be specified here by N. All right, so I want you to look at this and think about it. Energy sublevels are contained within the principal energy levels. So these are sublevels that are contained within the main principal energy levels. All right, so in other words, I've got my first principal energy level, n equals 1. It has one sublevel. N equals 2, my second principal energy level, has 2 sublevels. N equals 3 has 3. N equals 4 has 4. And 4 sublevels is the maximum number that you can have. So n equals 5, 6, 7, 8, all the way up would also only have 4 sublevels. Okay? So think about this question. When you buy tickets to a sporting event, which seats are the most expensive and why? So take a second to answer that question. All right, pause. And then unpause when you're ready, because I'm giving the answer right now. All right, so if you said the ones closest to the action, the ones that are closest to the front, the ones closest that are courtside or right there on the glass in hockey or right there next to the sideline or the end zone in football, then you've got it. Okay? The ones that are closest to the action are the most expensive. And likewise, the energy levels that are most close to the nucleus are going to be the ones that are filling up first. They're going to be the ones that are hardest to access and things like that. So there's a lot of parallels here that you can draw. Each energy sublevel relates to orbitals of different shapes. So there is one s orbital, and it's shaped like a sphere. Okay. There are 3 p orbitals, and they're shaped like dumbbells. You can have a dumbbell going along the x-axis here, a dumbbell going along the y-axis here, or a dumbbell going along the z-axis here. So same shape, just like 3 different orientations. Okay, and then there are 5 d orbitals that are shaped like double dumbbells. Okay, so you can have this kind of orientation, you can have this orientation here, this one here, or finally this one here. All right, so notice the pattern: 1s, 3 p's, and 5 d's. Okay, these are all orbitals where electrons can live. All right, there are also 7 different f orbitals, but you don't need to know the shapes of these. So each of them has a very different shape, and you won't need to know the shapes for the test or anything like that. I just need you to know that there are 7 f orbitals. So there was 1s, 2p, or 1s, 3p, 5d, and 7f's. It goes up by 2 every time. Okay? All right, so we're going to stop there for today. I'm going to make the rest of this slide a part 2. So this is where we're going to stop today. There's no homework for this lesson today. We're going to do our assignment after tomorrow's lesson. Okay, so thank you guys for watching. I hope some of this made sense, and I will see you later.